So before we start with the first subject, caches and memory systems, I would like to take you on a tour around the computer systems and first describe a little about how CPUs really work and also highlight some of the problems we will deal with in this course. So this is a crash course in computer architecture in about 45 minutes. About 30 years ago, this is the first CPU that I was part of designing. I did a couple of these circuits board on this picture. What you hear is what you see on this picture is one CPU and was super fast. The AXE supercomputer, a CPU controlling the telephone exchange of the company Ericsson. This was an amazing design. I actually picked some quotes from the marketing brochure that was printed 30 years ago. First of all, this CPU was 6 times faster than its predecessor, and it was also 1/6 of the size. So the floor space efficiency here went up with a factor of 36 just in one single generation. Also, it consumed about 1/5 the power of the previous CPU. So you can imagine this was a major leap. And then you can see some quotes here like 800,000 busy hour call attempts, should that ever be needed. So this is how we measure the performance of this machine, and we just could not imagine yet that you would ever need anything that was faster than this. But of course, we know that since 30 years back, performance has improved steadily. This CPU was running at 5 megahertz, and right now CPUs probably run about 1,000 times higher clock speed. So the CPU improvement has been steadily becoming faster and faster, and it seems to be going in an exponential rate. So if you plot this on a log scale, we see that this improvement is a straight line. This is sometimes referred to as Moore's law, but just to put the record straight, Gordon Moore never ever said that the performance of computers increase at an exponential rate. He simply said that the number of transistors you can put on a die increases with an exponential rate. You can put on a die with good economics was actually what this paper was about. Nevertheless, Moore's law often refers to this exponential growth. It's been going on for a long time, and it will probably be going on, increase at some rate for many years to come. So how do you get more efficient architectures? Well, traditionally, one of the safest way to get good performance was to increase the clock frequency, but you can also improve the architecture in that you can create and explore locality of some kind. We're going to talk about 3 different kinds of localities in this course: spatial locality, temporal locality, and geographical locality. You can also create and explore parallelism. And also here we have 3 different kinds of parallelism we will talk about: instruction level parallelism, thread level parallelism, and memory level parallelism. And then you can perform some speculative work, such as out-of-order execution, branch prediction, and prefetching. It is as simple as that. This is what this course will be about. However, increasing the clock frequency have turned out that for power reasons is not that easy to do today. So we will mention a little of why that is and what implications that has had on computer architecture as well in this course. Let's first take a look at inside the CPU and see what's going on. So a traditional way of executing instructions inside a CPU is what's called in load store architecture, where we have some instructions which are ALU instructions that performs operations on register values and store the result into register values. And then we have another kind of instructions, memory operations, that move data from registers to and from registers to and from memory. So for example, if we compile this simple code example here, C equals A plus B, the compiler would generate some of these instructions, load store instructions, to perform A plus B equals C. So the first instruction would be a load into R1 whatever value of A is stored in memory. So we will take some contents of memory, load into a named register, specifically register 1. The next instruction will load whatever value is stored in the memory location referred to as B, and that value will be stored into register 3. So once more, we will load something from memory, move it into a register. The next instruction is an add instruction that will add the value of R1 and the value of R3 together and put the result into R2. So here we will take values from R3, R2, R1 and R3 and send them through an arithmetic logic unit, which is a piece of hardware that can perform pluses and minuses and such operations. And the result will be put into a new register, which is register 2. Finally, we will store the new value stored in register 2. We will store that value to a memory location referred to as C. So as you see here, there are two kinds of operations. We have the memory accesses that moves values in and out of memory, and we have the ALU operations that performs the real work. And here we name two source registers and name one destination register where we want the value to end up. These instructions are executed incredibly fast on a computer. So these days, 3 gigahertz is a very reasonable clock frequency for a high-performing CPU. So 3 gigahertz, that means that every third of a nanosecond we will complete one instruction. That does not mean that it takes a third of a nanosecond to perform an instruction. It's just the rate in which we can complete instructions. Third of a nanosecond is a very short period of time, and in order for us to actually be able to do this, we have to split up the work of an instruction into many small pieces of work. And each small piece of work, it will be carried out by what's called the pipeline stage. So this is sort of like an assembly line. In assembly line, you don't build a single car complete and then you start to work on the next car. Instead, you will have one worker that puts the wheels on the car, and then the car advances to the next pipeline stage, and there will be a worker that puts on the motor, and then it advances to the next pipeline stage, and then will be a worker that puts on the steering wheel. It's the same thing with instructions. Instructions will progress between different pipeline stages. So for example, if you look at a specific instruction A here will first be in the I stage, and then we'll move to the R stage and the W stage, X stage, and then into the W stage. So these are in the very simplified example of the pipeline architecture, where the I stage is instruction fetch. The R stage reads register values, the X stage executes, and the W stage, pipeline stage, will write to register or memory. These are the pipeline stages. We also in this picture have some of the processor state that typically are the register values you saw from the previous slide, register 1, 2, 3, 4, 5, and 6, as well as some special magic registers that have special purposes, such as the program counter. And then we have the memory, and in memory we store the data and the instructions. We're going to look at how 4 very basic instructions are executed on this pipeline implementation. So first we're going to look at an instruction which adds register 2 and register 3 and puts the result in register 1. So what's going to happen here in the I stage is that we're going to fetch the instruction, the instruction from memory. That's always what happens in the I stage. In the R stage, we're going to read register values 2 and 3. So that's the 2 and 3 here. In the X stage, we're going to perform an operation. In this example, an add. So we're going to do the plus. And in the right stage, we're going to write the resulting value back to a register. So it's very basic 4-stage implementation of this instruction. If we load the value from some memory location into a register, what's going to be performed here are once more in the I stage, we're going to load the instruction from memory. In the R stage, we're going to read the register value 2 because we're going to need the register value 2 to calculate the memory location where we would like to load the value from. In the X stage, we're going to execute this plus here, where we're going to take the contents of register 2 we just read, and we're going to add that to a specific constant which is encoded in this instruction. And then at the W stage, we're going to read the value from that memory location into register 1. The store, of course, is very similar to load, just backwards. Here we would like to store value which is stored in register that it resides in register 2, and we like to store that to memory location identified by the contents of register 1 plus some constant again. So once more, instruction fetch, then we read register value 1 and 2. So in the execute stage, we're going to execute this plus, so we know which memory location we are supposed to store the value to. And then at the W stage, we're going to store the value from register 2 into that memory location. Finally, we have a conditional branch that says if register 1 has some property, for example, is larger than 0, then go to a new instruction which is stored in memory R2. Okay. So what we'll do here is instruction fetch. We fetch the instruction. Read, we read register value 1 and 2, so we can, and then in the X stage, we're going to make this comparison here. Is the value R1 larger than 0, for example? If so, we're going to change the value of the program counter, which is the special magic register that points to the next instruction to be executed. We're going to change the value of that register to instead have the value that was contained by R2. So this is the conditional store. We're going to see how these three types of instructions are used to execute a small basic block of a program. So the PC points to the next instruction to execute. So we're going to advance the PC pointing to the next instruction. And once more, remember the PC is actually just the register that's stored down with the other register values as part of the shared state. Now we fetch the green instruction during this cycle. Then we advance the PC to instead point to the gray instruction, and now we'll fetch the gray instruction. At the same time, the green instruction has moved into the R stage, and we're going to read whatever register values we need to read. So here we need to read register value C on the green instruction. PC advances, next clock tick, and now we're going to do this in the green instruction is in the execute stage. We're going to perform this plus operation here. The gray instruction is in the R stage, so we're going to read register A, and the pink instruction have just been fetched, and so on. Now we have the brown instruction being fetched. The pink instruction will perform read register C. The gray instruction will actually perform this plus over here, and the green instruction will perform the load operation from the memory location into register A, and so on. We advance the execution here, and eventually the brown instruction comes to the last pipeline stage, and now we can actually change the program counter, which says we should go back and to the same instruction A again. So this is how we executed this loop with 4 instructions. There are a couple of problems here in this execution. One problem was that actually the execution was wrong. The value that we executed, the purpose of this program was not fulfilled because we made some errors in our execution, and that is because an instruction writes to a register in the write phase stage, and it reads in the read stage. So what happened here was that we had 2 data dependencies. So the result of register of the green instruction was actually used immediately by the gray instruction. So from register A to register A, and from register C to register C. So here's another data dependence between the pink and the brown instruction. The problem is that when the gray instruction reads the value of register A, that value has not yet been updated by the green instruction. So in order for us to execute correctly, we actually have to introduce what's called a stall in the pipeline. We have to wait a little longer until we start the gray instruction. We have to also wait a little longer until we start the brown instruction. We also saw another problem here, which was that immediately after we executed the brown instruction, we cannot tell. The cycle that pointed to the brown instruction, we don't know whether or not we should go back to instruction A or we should execute the very next instruction, for example, maybe instruction E. So it takes many cycles until the brown instruction is in the final pipeline stage. So that introduces even more stalls in the pipeline where we simply don't know which instruction to execute next, and this is referred to as branch delays. So this simple 4 instructions actually took us 9 cycles to execute instead of what we had hoped that they would execute complete 1 instruction every cycle. So in order for us to execute code with better efficiency than this, we have to find instructions with lots of instruction level parallelism. We have to have instructions that not depend on each other. So there can be no control dependence, which is you don't like the branches, and there can be no data dependence between instructions in order for us to work on many of them in this pipeline in an efficient way. But it's actually a lot worse than that, because in modern pipelines we don't only start 1 instruction every cycle, we tend to start several instructions every cycle. So in, for example, this machine I have in front of you, it starts like 3 or 4 instructions every cycle. That means we actually have to find 4 times more instruction level parallelism, 4 times more independent instructions in order for us to keep that pipeline happy. But it's a lot worse than that, because modern CPUs don't have 4 pipeline stages. They typically have like 20 pipeline stages. And that means that there are a need to find even more independent instructions in order to make that modern architecture happy. But it's actually a lot worse than that. The memory sits far, far away, while the CPU can complete an instruction every third of a nanosecond. It takes maybe 60 or 70 nanoseconds to bring some data in from memory. So it's sort of like a 150 or even 200 cycle delay each time you want to bring something from memory. So that means that these data dependencies that I, in the previous simple example, forced us to install a pipeline stall will actually need to insert 151 pipeline stalls every time there is a dependence. So what are the fixes here? Well, one fix is what's called an out-of-order execution. So if we have this piece of code, we have a basic block here, then we have some kind of condition, we may jump back again, or we may go to some other basic block, and we see that there is a data dependence between this memory, this load, and the following instruction, the add instruction, because we want to reuse the value of register 1 here. Instead of stalling the pipeline, waiting for that to happen, we could start to execute the very next instruction, because it looks like it's not dependent on the first 2 instructions. And also the 4th instruction seems to be independent of the other 2 instructions. So this out-of-order execution is a way to actually execute the instructions of the basic block in a different order than the compiler told us to. So we will start the instructions in a different order. We have to make sure that the side effect that each instruction has on the state of the machine is actually performed in order. So out-of-order execution, but still the effects, the side effects are in order. Second fix is that we're going to take help from a little green man. We're going to design a little device called branch predictor. It's going to guess whether or not a branch is taken. That means instead of stopping at the branch instruction, waiting in the modern pipeline for maybe 20 cycles until we know the outcome, this little green oracle is going to guess whether or not the branch is taken, and will allow us to start executing instructions of the next basic block before we know the outcome of the branch, just based on the guess. once more, we have to make sure that this speculative execution that's taking place down here will not have any side effects on the state until we are really sure that that branch is taken. We cannot start to apply side effects just because we made a guess that the execution will continue down here. A third fix that we're going to do is to actually do both of these tricks together. We're going to have the little green man predict a path that we think is going to be taken. And then we're going to look at all the instructions along the predicted path, and we're going to apply out-of-order execution on all those instructions. So let's say that we get, have a long latency load into a register as the first instruction here. Instead of stalling the pipeline, we can go on and start working on the next instructions of the same basic block, but also start to work on instructions in some other basic block, hoping that this prediction the branch prediction will be correct. And now and then we're going to make the wrong prediction. And when the wrong prediction happens, we have to make sure that the side effect of that speculative work is not applied to the state of the machine. And also we cannot do change any register values or change any memory values until we're really sure that we are supposed to perform that piece of work. That was fix number 3. Fix number 4 that deals with the problem that the memory sits far, far away. And that is solved by the introduction of caches. So cache is like a little scratch pad, small memory, scratch pad memory, in which we can store some values that we think will be needed soon by the pipeline. Okay, so it's a small, we store some values that we recently have accessed in this fast but small memory called the cache, and hopefully if we access the same values again, then we can access them with a much shorter access time. The 5th fix is what's called a hardware prefetcher. Once more, we're going to ask a little green man to try to figure out and guess what piece of data we will be requesting in the near future. And that little green man will bring those pieces of data from memory and put them into the cache even before we have asked for them. Another problem that we have running into has been that the power consumption has been going up too much, and that is the power consumption is very much related to the frequency with which we run the processor. So instead of just increasing the clock frequency, we will have a different approach of getting faster CPUs. Well, that's what's called multicores. So nowadays, inside one of these CPU chips, we will not have just one CPU, but we will have several CPUs working in parallel. So each of the CPUs here have their little caches and so on, and they're all connected to the same memory. But now we have to start to deal with and handle new problems that comes from what's called thread level parallelism. So in order for these CPUs to work together on the same kind of problem, we have to create some kind of thread level parallelism, and that also increases new problems that we need to fix. One such problem is coherence. So let's say that this CPU over here has in its cache storing the fact that x is equal to 0, and some other CPU also stored in its scratch pad memory stored the fact that x equals 0. So what happens now if the CPU to the left wants to change the value of x? Well, we cannot let the old and boring value of x reside in this other cache, so we have to implement what's called coherence. So coherence, for example, could automatically go out and invalidate any stale copies that we have around sitting in other caches. So that's fix number 7 is coherence. Fix number 8 is when you is solving the notion of time or ordering in this machine. So as I said before, these CPUs work incredibly fast. They all execute code, new instructions every third of a nanosecond. So it's very likely that some of them perform operations at the same time or almost at the same time. So here we have a CPU to the left changing the value of x to 1, and the CPU to the right here changing the value of y to 1. For some execution, it's very important for us to be able to determine which of them happened before the other. But this is a tricky thing to implement. We don't want to completely order all the parallel activities in the machine. So we have to apply something called memory modeling. So we have to define what time means and what order means in this architecture. We're going to deal with that as well. Also, another problem that has to do with multi-threaded execution is that if you would like to have some kind of atomic activities in the machine, so if let's say we would like to update the value of y and the value of x at the same time, happening as an atomic activity without anybody else being able to snoop in and see that y is equal to 1 while x is still equal to 0. And in order for us to give those kind of tools to the programmer, we have to implement something called synchronization. So we're going to talk about how to implement this, what's called critical regions. Finally, we have to make it fast. So all these things have to work very fast. And here's an example of a chip we're going to talk about in the tail end of the course. It's a chip that was released last year by Intel called Xeon Phi. Here we have about more than 60 of these CPUs, or as they are referred to here as cores, each of them executing x86 instructions. Each of these cores actually executes instructions from 4 parallel threads. So it's a total of more than 240 parallel threads executing in this architecture. Okay. Each of those instructions executed in parallel is capable of performing 16 multiplications in parallel. So there's lots and lots of parallelism, and we have to make sure that this can all work efficiently and scale well. So that ends this crash course, and I don't expect anybody of you to follow and understand all these issues and tricks we talked about, but just give you a little flavor of what we will be dealing with in this course moving forward.